A pleasant day to everyone. We are Group 1, and in this presentation, we are going to discuss Schrödinger's equation and particle in a box. This discussion includes various subtopics. The presentation will start with the discussion of Born's interpretation of the wave function, which will be followed by the normalization. The next subtopic will dive deeply into Schrödinger's equation followed by the particle in the box problem, and lastly, the average value. So let's begin. Schrödinger's equation is an important fundamental equation in the branch of science known as the quantum mechanics, which is the study of submicroscopic phenomena. It was developed by an Austrian physicist, Erwin Schrödinger, on the year 1926. This equation was used to introduce us the term wave function, which is also important in quantum mechanics. So what is this wave function? What does it mean? What does it tell us about? There have been many different interpretations of the wave function about its representation. According to Schrödinger's interpretation, the wave function psi represented the particles that disintegrate all over space, which means that wave function tells us the location of the particle, for an example, an electron that was spread out through space. To Schrödinger, wave function can be interpreted as the charge density of an electron that is spread out through space. It means that within a wave's amplitude, there's a fraction of the electron that can be found. And the higher the amplitude, the higher its charge density, meaning that we can find more fraction of that electron within that amplitude in the wave. However, Schrödinger's interpretation of the wave function did not work so well and was later abandoned. This caused problems to other physicists and even to Schrödinger himself, who came up with this equation. So during this conundrum, a guy named Max Born came into the picture. He was a German physicist that proposed his own interpretation of the wave function, which later became known as the Born interpretation of the wave function. According to Max Born, the wave function represents the probability of finding a particle or an electron within a region in space. Rather than giving the exact location of the electron, it tells us how likely it is to find the electron within a particular region in space. So rather than the charge density, Born interpreted the wave function as the probability density, which is the relative frequency of finding the electron within a region. The square of the absolute value of the wave function is equal to the probability density, which is the complex conjugate of psi times itself. And in the equation below, it tells us that the probability of the particle being inside the area dx. So like the charge density, the probability density is proportional to the square of the amplitude of the wave, which means that the higher the amplitude, the more likely the electron could be found within that region. Here in this graph of the wave function, in these regions we have the higher amplitude. It is more likely for us to find the electron within that region. However, in this region that has a lower amplitude, it is less likely for an electron to be in that region. Now remember that the wave function and the probability density represents the probability of finding or locating an electron within a region in space. So it doesn't mean that we can always locate an electron within a region with high amplitudes, nor does it mean that we can't locate an electron within a region with low amplitudes. We can still locate an electron within a region with a small amplitude. However, it is less frequent compared to the other region with a higher amplitude. So basically, the wave function psi is, according to Born's interpretation, represents the probability of locating the whole particle or electron, not its fraction, the whole particle. The square of the wave function is equal to the probability density proportional to the square of the amplitude of the wave, meaning that the higher the amplitude, the more likely it is for an electron to be found within that region. And that's about it. And that's about the Born interpretation of the wave function.
The Born interpretation suggests that there should be another requirement for acceptable wave functions. According to Born's interpretation, the probability P of an electron being in a certain region between points A and B in space is expressed in equation 1. Meanwhile, equation 2 shows that the probability of a particle having wave function C can be evaluated over the entire space in which the particle exists, which then the probability should be equal to 1 or 100%, which is exactly the normalization condition. The electron must be somewhere, so when we look everywhere, we find it with a probability of 100%. Normalizing a wave function just means multiplying it by a normalization constant, denoted by the capital letter N in here, to ensure that the sum of the probabilities for finding a particle is equal to 1. Mathematically, this means integrating psi star psi over all space should equal to 1. To see a pictorial example, consider n equals to state for a particle in a box of length L equals to 1. The unnormalized wave function is just psi of x equals to sine 2 pi x, while the normalized wave function has a factor of the square root of 2 in front of it. After plotting the two equations, it gave the same shape for the two wave functions but different amplitude, wherein the normalized one has a higher amplitude. Evaluating the integral of psi star psi over the entire length of the box gave a probability sum of 0.5 for the unnormalized curve, while 1 for the normalized. The result on a normalized one could be attributed to a physical distribution making only 50% probability of finding the particle somewhere in the box. So the process of normalizing is just multiplying it by a normalization constant that guarantees that the probability of a particle existing in all space is 100%. So to do this in practice, let's evaluate the previously given integral. First, we will substitute sine 2 pi x to psi star psi in the integral equation, which will be evaluated from a length of 0 to 1. Solving the integral will give us a value of 1 half or 0.5. Therefore, this wave function is not normalized since it should be equal to 1 to be considered normalized. To normalize the wave function, we need to multiply it with a normalization constant, which is denoted by the capital letter A in this example. Now, plugging in the value for wave function, we can evaluate the integral and we should come up with an answer of a squared over 2. Since we want it to be normalized, we will make the integral equal to 1. And solving for a will give us square root of 2. And now, our normalized wave function is psi of x equals to square root of 2 sine 2 pi x.
The Schrödinger equation is postulated. It is not derived, yet the predictions based upon it are verified via experiment, such as the Davison-Germer particle diffraction experiment. This raises the question, what is the nature of the wave? We respond in retrospect that the wave is the wave function for the electron. So we shall first postulate the wave function for a simplest conceivable system, which is a free particle. We can see that a pure sinusoidal wave can be represented by this. And this makes use of the de Broglie relationship between wavelength and momentum and the Planck relationship between frequency and energy. Now, the harmonic wave is just as good as a representation of a free particle as the pure sinusoidal wave, and so is its superposed solution. It is easier to show the relationship to the Schrödinger equation by generalizing this wave function to a complex exponential form using the Euler relationship. We fix the time so we can concentrate on the spatial variation. Then this will be our wave function. Now, from the de Broglie relation, the kinetic energy is equal to p squared over 2m and is equal to h bar squared times k squared over 2m. Therefore, this will be our equation. For a free particle, the potential energy U is 0. Therefore, the total energy E is equal to the kinetic energy K. If the potential energy is not 0, then K is equal to E minus U, and substituting in the above equation gives us this, which is the time-independent Schrödinger equation in one dimension. So far, we have suppressed the time dependence, but the general form of the Schrödinger equation is known as the time-dependent Schrödinger equation. When the potential energy is independent of time, wave functions satisfying the time-dependent Schrödinger equation in one dimension can always be written as this, where psi of x satisfies the time-independent Schrödinger equation and omega is equal to E over h bar.
Now that we've seen how the Schrödinger equation may be used to solve the energy of a particle moving freely along a line, let us now consider what happens if we restrict the movement of the particle to only a portion of that line. This problem is usually referred to as the particle in a one-dimensional box and is a common application of a quantum mechanical model to a simplified system consisting of a particle moving horizontally within an infinitely deep well from which it cannot escape. The solution to the problem gives possible values of E and the wave function that the particle can possess, of which when squared gives us the probability of locating the particle at a certain position within the box at any given energy level. To solve the problem for a one-dimensional particle in a box, we must follow our big recipe for quantum mechanics. First, we need to define the system as well as set the boundary conditions. Next is to solve it using the Schrödinger's equation. And lastly is to define the wave function and allowable energies so that we could arrive at a solution to the particle in a box. Let us consider a particle of mass m that is confined to a one-dimensional box of length L. The potential energy is 0 inside the box, represented by V equals 0, and goes to infinity at the walls of the box. We assume that the walls have infinite potential energy to ensure that the particle has zero probability of being at the walls or outside the box. The time-dependent Schrödinger equation for free particle is represented by this equation, equation number 1. So this equation can be modified for a particle of mass m free to move parallel to the x-axis with zero potential energy everywhere, resulting in a quantum mechanical description of free motion in one dimension as can be seen in this equation number 2. We can take this to yield a general equation shown in equation number 3 where a, b, and k are constants. By applying the boundary conditions we have earlier to the general equation, we can now solve for the constants and plug them back in. So by doing so, we define the wave functions represented by equation number 6. By solving k in equation number 3, we found out that the solution to the particle in a box is given by this equation, equation number 7. So as can be seen here, energy as a function of quantum level turns out to have only discrete integer values given by this, wherein n is equals to 1, 2, 3, etc., and no other values. So the value of the particle is said to be quantized and the energy n is called the quantum number. Note that the quantization arises naturally from the boundary conditions that we've set earlier, and the energy is inversely proportional to that of the mass and length of the box. Several important conclusions can be drawn from this model. As we've said before, the kinetic energy of the particle is quantized. Second, the lowest possible energy of the particle is not actually 0, but is equal to the left-hand side of this equation. This is called the zero-point energy and means that the particle can never be at rest because it will always have kinetic energy. This is also consistent with that of the Heisenberg uncertainty principle, because if we have a particle that has a zero energy, we would know where it is in both space and time, but we all know that is not the case. Also, the square of the wave function gives us the probability density. In fact, this density wave function looks like just like a standing wave that is set up in a vibrating string but have positive values. Also, the energy of the system is inversely proportional to that of the mass and the length of the box, and the quantum mechanical solution shows that there cannot be a uniform probability density for the molecule. Here we have a particle in a box wave function plot that was done in Desmos under some various conditions. So plotted in here are different things. So here we have the wave function plot that is represented by this half sine wave in blue. We also have the probability density represented by this violet, and as well as the energy as a function of n in this green line. Okay. On the sides, you also have these small green lines. As you can see here, these are the energy of the orbitals. For example, n equals 1, n equals 2, n equals 3, and so on and so forth. So if we vary the parameters, say let's start with the n. So if you've got a n equals 1, we have a half sine for the wave function and one hump as well for the probability density. If we increase n equals 2, now we have here a full sine wave for the wave function and two humps for the probability density. If we increase n to 3, we have here for the wave function positive, negative, positive, and 3 humps for the probability density plot. Okay, the same trend is also prevalent if you increase the n. Okay, for L is in the denominator, so there is a inverse proportionality with the individual energy states of the of the box, and as the L increases, the energy states becomes compact, but as you decrease the L or the length of the box, the energy increases. Okay. For M, it has no effect to the wave function, but it does an effect on the energy. So as the mass of the object gets smaller, quantum behavior becomes more apparent and the energy differences becomes more separated. As the mass becomes bigger, energy levels gets closer and the quantum effect goes away. So that's the basics for the particle in a box wave function. One application of 1D particle in a box is on UV vis spectroscopy. Let us consider the molecule butadiene. So this molecule has a delocalized electron in this conjugated system. By using the BIB model, we can make predictions on energy transitions that can occur in this molecule. To be able to do this, the first thing that we need to know is what's the length of the box. In this case, what's the length of butadiene? We can calculate that by using its bond lengths, and it turns out to be 578 picometers. Second, we need to know the number of electrons that goes into this. Butadiene has 4 pi electrons, which occupies the 2 lowest energy pi orbitals when in ground state. In terms of n, we would expect that a electronic transition from 2 to 3 would occur. If we can calculate the energy difference between the two, we can compare that to the actual value of photons that will be absorbed by butadiene. The energy difference equation is equal to the energy of n equals 3 minus the energy of n equals 2 using the equation that we previously derived. And since we already know the mass of the electron, and by using some relations that we already know, such as the speed of light and Planck's constant, we can rearrange the equation to solve for the wavelength. And if we plug the values and solve for it, we end up with 220 nanometers as the wavelength needed to make the transition from the second to third energy level. And this is pretty close approximation to the experimental value of 217 nanometers.
For calculating of expectation values, the integral over all space of the probability density function gives us a value of 1 for a normalized wave function. This 1, which is the maximum value possible, tells us that the probability of finding the particles somewhere in space is 100%, which makes sense since the particle has to exist somewhere. And now, if we want to determine where it is most likely to find the particle, we have to perform a similar calculation. We will need to use the position operator. The operator will be placed in between the psi star and psi, and this depression will be equal to x0. x0 is an expectation value. It is a number in which this case tells us the most probable location of the particle. In statistics, an expectation value is a weighted average of a variable. For instance, we want to measure the variable x, but it does not have a definite value. It exists as a distribution of values, something in which will be true of all the time in quantum mechanics. The expectation value is the weighted sum of all possible values that x can take times their respective probabilities. Mathematically, the integral over all space of psi star times the position operator acting on psi. This is how we define the expectation value of the x-coordinate at a given time t, which is written this and read as the expectation value of x with wave function. Next, we can also write an equivalent equation for the momentum operator, whereby the expectation value of p equals the integral over all space of psi conjugate and the operator p acting on psi. We can rewrite this using the definition of the momentum operator, which is negative I times h bar times the partial derivative with respect to x. And lastly, we can write all the dynamical variables as functions of position and momentum. This means that it is possible to find the expectation value of any dynamical variable q by calculating this way, with the expectation value of q of x and p being equal to its expression. Let's apply this specific example to kinetic energy. In the classical physics series, we learned that the kinetic energy of an object, which from now on we will represent as t, is equal to 1/2 mv squared. Since momentum equals mass times velocity, if we just put an additional mass in terms of both the numerator and denominator to keep the expression equivalent, and we can change m squared v squared into mv, quantity squared or p squared, leaving us with p squared over 2m. And now, we can take this classical equation and translate it into quantum equation by replacing momentum with the momentum operator. Let's then put it in our expression for the momentum operator, putting it out front, but twice, since the operator is squared. Now, to simplify, negative I times negative I gives us I squared or negative 1, so let's just cancel it out and make the whole expression negative. Then, we can pull the h bar squared up, and after that, the partial derivatives will be multiplied to give the second derivative with respect to x. This will give us the quantum operator for kinetic energy. Lastly, let's find the expectation value for kinetic energy for a given wave function psi. As we learn to do this, we place the operator t in between the bra of psi and ket of psi. We can then replace the operator with the expression it represents, and we can get the integral of psi star times the kinetic energy operator acting on psi dx. Now, we can recognize that we have the same constants with h bar and mass, so let's pull out this of the integral. That leaves psi star times the second derivative of psi with respect to x dx. So, we can now calculate the kinetic energy of a quantum particle given its wave function.